hopefully it should take about half an hour. Okay, so this is, we're going to take a little divergence a little bit and do a very simple problem. This is a computation in nature, so I'm just going to cover it anyway. So we covered in class when we took a look at machine learning system design, we had what was known as a confusion matrix. Okay, so what a confusion matrix does is that it, when you have a binary classification problem, we usually split up the classification when you're comparing the predicted and the true output to, into 4 different classes. Okay, so what we're doing here is we have a bunch of questions that we have to figure out what the actual numbers are from the table. So when you're talking, what we have to do is you have to calculate what is known as the number of true positives. So a true positive is when the predicted and true are both equal to 1. So a true positive means that what you predict and what the actual output is positive. It is what is known as the true positive. In this case, it's just this element right here. So when both y is equal to 1 for the predicted and the output, it's just equal to 10. Okay? A false positive is when you predict true, but the actual output is false. So it's like saying that you have cancer, but you really don't. It's kind of a shitty thing to tell someone, right? So the predicted is 1, but the true is 0. Thank you. Okay? So the predicted is 1, the true is 0. In this case, this is equal to 5. All right? Now we have to take a look at false negative. So false negative means is that we say that you don't have cancer, but you really do, which is probably even worse off than saying that you have cancer, but you don't. It's like, one's a practical joke and one means that you're screwed. All right? So false negative means that the predicted is 0, but the true is equal to 1. So all you have to do is just take a look at this column here. So the predicted is 0, the true is 1. In this case, this is equal to 7. All right? And true negatives, you can pretty much infer from that. It's saying that what we predict and what it actually is both negative. It's both equal to 0. Okay, so true negative is when predicted and true are both equal to 0. In this case, it's equal to 20. That's good. Okay, so what precision means is that how you calculate precision is very simple. You basically take the number of true positives and divide by the total number of true positives and false negatives. Okay, so in this case, this becomes 10 divided by 10 plus 7, which is 10 over 17, and in percentage, this is equal to, not false positives, not negatives. Sorry, my bad, false positive. I was like, that doesn't look right. So 10 over 15, which is 66%. Okay, so what precision means is that out of all of the examples that you classified as positive, how many of them were actually positive? That's what precision means. Okay, recall is defined as the ratio of the number of true positives over the number of true positives plus false negatives. Okay, so this is equal to 10 divided by 10 plus 7, which is 10 over 17, and this is roughly about 58% or so, 58.8%. Oopsie. Okay, so what this is saying here is that you were, out of all of the entire examples in your training set, you only were able to classify 58% of them accurately. Okay, so precision and recall are a little different in that regard. So the F1 score is, once you have the precision and recall, you want to combine them in a uniform measure that calculates the total accuracy of your classification system. In this case, it's simply 2 times the precision and recall divided by precision plus the recall. Okay, so when you calculate this, it's roughly 62.5%. Okay, so then the next part of this question asks you what would the performance of this be? So comment on the actual performance. So if you take a look here, so what we're saying here is that the precision, out of all the examples that we classified as positive, only 66% of them are correct. Okay, so out of all predicted positives, okay, positives, only 66% were correct, and that's pretty bad. I wouldn't put faith in this actual system. Okay? Okay? And when you talk about recall, what recall implies is that out of everything that you've managed to correctly, out of all of the total examples in your system, you only managed to classify 58% of them correctly. Okay, so that's what it actually means. So in terms of all positive, so that's the recall. So we only managed, so this is 1, this is 2, only managed to correctly classify 50% of all positives. So correctly classify 58% of all positives. So that's what the recall means. Okay? So therefore, I would consider it a bad system. Like having a 60% classification accuracy is almost as bad as flipping a coin and saying, hey, whatever the coin says, that's what you're going to get. So it's almost as bad. I wouldn't put faith in the system if it was me. Okay, so just very simple computation. Just wanted to get that out there. Okay. Okay, so we have 2 more examples to cover. So this one is going to deal with k-means, and the last one will be self-organizing maps to end the review. Okay, so this is week 9. So we have the following set of data for k-means. So this is coming from the problem set, week 9. So we see here that we have 6 examples with 2 features. Okay, so what we want to do is we wish to find 2 clusters. We want to figure out that there are 2 clusters, and we want to determine the cluster centroids and the memberships per element. Okay, so find memberships and centroids for 3 iterations. Okay, so we're going to do this 3 times. Okay, so the initial centroids, are equal to, so the first one I have as -1, 2. The second one I have as -1, 1. Okay? Okay, so just to verify, one part of the question asks you to actually plot this and verify that you can actually split this up into 2 clusters. Okay, so this is the first part. First part's very simple. All you have to do is just plot this. So the dynamic range for each of the features only goes between plus and -2. So it's going to be pretty easy to draw this. Okay? So we have -1, -2, 1, and 2. And all you have to do is just, plot each of these. This is the first feature. This is the second feature. Now, -2, 2 is over here. This is the first one. And then we have -2, 1.5, which is over here. And then we have -1.5, 1, which is over here. Okay, so this is the first 3. And then the last 3 is 1, 1.5, which is here. 1.5, 1.5, which is here. And 2 and 2, which is here. So you can clearly see that there are 2 clusters of data. Like, if the initial centroids were -1, -2, so we have this guy. This is mu1, okay? And this here is mu2. All right, they're actually quite close together, but I did that on purpose so we can actually cluster things. But we can see that there are certainly two clusters. So our objective is to figure out the centroids and the memberships so that it will separate this data into 2 different clusters. Okay, so you just, you're currently doing the k-means log now, so just to make sure that we're on track, let's go ahead and calculate this. So the first step that you need to do is we have our initial centroids. What you have to do is you have to figure out the memberships of each of your examples. So for each example that you have, which of these examples, which centroid is each example closest to? And whichever centroid is the closest, that is the membership that you define for that particular example. Okay, so we're going to do the first iteration. Okay, and what we're going to do is we're going to calculate the memberships. Okay, so as we go, I'm gonna put this example chart here, so I don't have to keep scrolling back and forth because it's actually quite distracting. Okay, so we need to do the first example. So the first example is equal to what? It's equal to -2, -2. Okay, so what we need to do is, okay, so let me just write down the centroids, -1, 2, and -1, 1. Okay. What we have to do is for each of these centroids, we have to figure out the distance between this example and each of these centroids, and whichever has the smallest distance, that is the membership you define for that example. Okay, so let's calculate the distance between the first example and the centroid. Okay, it's just Euclidean distance, so you just take each of the components, so -2 subtract -1 squared, plus -2 squared, right? So these here, this is for x of 1, okay? And this is for the centroid, okay? So when you calculate that, just double checking, yep. So in this case, when you calculate this becomes plus, so what you actually get is square root 17, okay? So what I like to do to save time is I just like to calculate what's underneath the square root, because when you have a number here, all you have to do is just check to see whether or not the number is smaller. There's no need for you to calculate the square, just leave it inside the square root to save time, okay? So now you calculate the distance between the first example and the second centroid, okay? So in this case, we have -2 minus -1 squared plus, and then -2 minus 1 squared, okay? So remember, these two things are the example, right? And these two are the centroid, 2, okay? So when you calculate this, the number we get here is square root 10, okay? So we have 3 squared and then 1 squared, so root 10. So which of these are smaller? So obviously, square root 10 is smaller than square root 17. So the membership for example number 1 belongs to cluster number 2, because the smallest distance is to the second centroid, okay? So D2, so let me see here. So square root 10 is less than square root 17. Therefore, the membership for the first example belongs to cluster number 2. Okay? So this is saying that the membership for example 1 belongs to cluster number 2. Okay? All right? So let's do it for the second one. Very simple. So the second example we have is -2 and -1.5. Okay. So now, just as before, the centroids were equal to -1, 2, and the next one is -1, 1. So all you have to do now is figure out the distance between each of these each centroid and that example. So find the distance between the second and the first centroid. Okay, so in this case we have -2 minus -1, okay, and then plus -1.5 minus 2. Okay, in this case, when you calculate this, this one is equal to 13.25, okay? And when you calculate the distance between this second example and this next centroid, okay, we get -2 minus -1, okay, plus -1.5 and subtract 1, okay? When you calculate this, it gives you 4.25. Not 4.25, it's 7.25. Okay. So which of these is smaller? Obviously this one here. Okay, so this is the smaller one. So what does that mean? This means that example number 2 gets defined as membership to belong to cluster number 2. Okay, so you choose whichever cluster centroid is the smallest, and that is the membership that example belongs to. All right? Do the third one. The third one, okay, I'm going to put that picture in again because I'm tired of scrolling back and forth. So we have this guy. So 3 is, we have -1.5 and -1, transpose, okay? It's a column vector, I just want to write that out. And we want to find the distance, okay? So the distance between the third example and the first centroid is equal to what? So we have -1.5, -1 squared, okay? Plus, and then we have -1, subtract 2 squared, okay? So when you calculate this number, okay, this is equal to square root, and we have 9.25. Okay, it makes sense because this here will be 3 squared, and 1.5 plus 1 would be -0.5. When you square that, it's 0.25. When you add that up, it's fine. Okay, calculate the distance between the third example and the other centroid, okay? Which is what? This is equal to -1.5 subtract -1 squared, right? And then plus -1 subtract 1 squared. When you calculate this, you get 4.25. Okay? So which of these is smaller? Obviously the second one again, because we have a smaller distance to the second cluster, second centroid in comparison to the first. So therefore, the cluster membership for example 3 is equal to 2 again, okay? All right, let's do the next example. Yeah, this one's a breeze compared to the neural network stuff. Lots of matrix multiplication, that sucks. So this is a nice breather. comparison to what you've seen before. So this next example is 1.51, okay? And again, the centroids are equal to -1, 2, and -1, 1, okay? So let's calculate the distances. Okay, so you take the fourth example, figure out what the distance is between that and the first centroid. So you have 1.5 minus -1, okay? And then plus 1 minus 2. Okay, so when you calculate this, this actually becomes 7.25 because 2.5 squared is 6.25, and then you add that with 1, you get 7.25. Okay, so let's do the next one. Okay, so when you do this, all right, you get 1.5 minus -1 squared, okay, and then plus, let's see here, 1 minus 1. So that obviously goes away. We're left with this one, which is equal to 6.25 square root. So obviously this one is a smaller one, so this is the smallest one here. Okay, so what that means is that the fourth example gets assigned to cluster 2. So the membership for that is 2. Okay? All right, let's do the next one. This is equal to 1.5 and 1.5, all right? In this case, you want to find the distances yet again. So take the distance between the fifth example and the first centroid. In this case, this becomes 1.5 minus -1 squared, okay? Plus, and then 1.5 minus 2 squared, okay? Yes, yes. So when you calculate this, just want to be sure I got this right. Yes. In this case, this we get 6.5. Okay, so now this becomes 1.5 minus -1 squared plus, and then we have 1.5 minus 1. Okay, so this is where I screwed up, but I'll show you how to fix this. So if you take a look here, you will not get this case for the final exam. I will make sure that the distances are unique, but you may get a point where these two distances are equal. Okay? So there are many ways to figure out which cluster to go to. What MATLAB does, and what you're doing now, is you choose the cluster where it is the smallest distance the first time you encounter it. Some people like to randomly choose. Other people like to, perhaps, they like to do different things. They like to either randomly choose or either the first time they encounter it or the last time they encounter it. But in this case, for our particular purpose, what we're going to do is you choose the cluster where it gives you the smallest distance the first time you find it. So because we've found this distance the first time to be part of the first cluster, we're going to assign that cluster membership to be part of 1. Okay? So let me just write that down. So if you won't get this for the final, I will make sure that the distances are unique. So if the distances are equal, okay, you can either randomly choose the membership because it can fit into either one. So randomly choose the membership or choose the first centroid to produce the smallest distance. Or last. But we're gonna choose the first one, but I will make sure that the distances are unique, so there's no ambiguity. Okay? So we're going to choose the first time that we've seen this calculation. So we choose the first time. So whichever centroid gave you that distance the first time you encounter it, that's when you choose. So in this case, the membership would be 1. Okay, that's what we're gonna do that to make this example work. Okay? Then finally, you want to calculate the distance for the last example, which is 2, 2. Okay? So let's just do this. So we have x of 6 between that and the first centroid. So in this case, we have 2 minus -1, right? And then plus 2 minus 2. Okay? So in this case, we have square root 9, which is 3, obviously. And then you want to calculate this with the next centroid. I remember this. I remember these centroids now, so it's it's pretty standard. Not standard, but it's remember from short-term memory. So we have -1, and then we have 1 instead. So we have 2 minus 1. Okay? So in this case, this becomes square root 10. So this one here is the smallest. So this, because that is the smallest, the membership that you give this belongs to cluster 1. Okay? So far we have the first 4 examples belonging to cluster 2, and the last 2 examples belonging to cluster number 1. So just to recap, we have these 4 belonging to the second cluster, and these last ones belonging to the first one. Okay? So now that we've figured out what the memberships are, what we have to do next is we have to update the centroids, right? So we have to update the centroids now. So how you update the centroids is very easy. All you have to do is just take all the examples that belong to the cluster that you assign the membership to, and just find the average of all the features for each of those examples, and that is the actual updated centroid. So if you want to update the first centroid, if you take a look, we see that examples 5 and 6 belong to the first cluster. So you want to find the average. So there are 2 examples in this cluster altogether. So you have 1 over 2, and then x of 5 plus x of 6. Okay, so that is the update step. So 1 over 2, x of 5 was equal to, we had 1.5, okay, and 2. So when you calculate this, what the actual output is that it will be, I think it's 1.875 or something like that. So, yep. So it's 1.75, sorry. So this would be the updated centroid. So it was originally at -1.1. Now it's moved over to 1.75, 1.75. That's the first centroid. The next centroid is the first 4 examples, and then you find the average of each of the features like that. So take the first 4 examples. Okay. In this case, we have 1 over 4. So let me see. It was -2 minus 2 plus -2 minus 1.5 plus minus 1.51 minus 1 and 1.51. Okay. So if you calculate this, well, you see that the negative and positives cancel. You have -2 and -2, which is -4 divided by 4, so you have -1. And we have -2 minus 1.5 minus 1 for 4 divided by that is equal to, let's see here, is it minus 0.875? That isn't, okay, I'm just double checking here. So -2, oh, sorry, it's +1. Yeah, so 1, okay. So then these cancel as well, right? I didn't see that there. So when you do this, you get minus 0.875. Okay, so this would be one full iteration of k-means. So you find the cluster memberships, then you find these centroids. So we're going to do this one more time, okay, with these updated centroids, and then I'll leave the last one for you to do that on your own, because I want to cover the self-organizing maps example. Okay, so iteration number 2. Okay, iteration number 2. Let me just put down, this stuff again. All right. Okay, so my centroids, the updated ones, were 1.75, 1.75. Okay, and this one was equal to -1 minus 0.875. Okay, so what I need to do now is I have to figure out what the centroid memberships would be for each of the examples one more time. Okay, so what I need to do now is I need to find the distance. So this is the first training example with the new updated centroid. Okay, so in this case this is -2 minus 1.75 squared, okay, plus -2 minus 1.75 squared again. Okay, so when you calculate this, this becomes, let's see here, so minus, so this is actually quite a large number. This is 28.125. Okay, so when you calculate the distance to the next example, the next centroid, okay, so this becomes, okay, so we have -2 minus -1, okay, and then plus -2, and then minus, okay, this is equal to, and then we have 2.265. Okay, so which one of these is smaller? Obviously this one, this is smaller. So what will happen is that the centroid, the membership, is assigned to cluster number 2. Okay? Okay, so what I'm going to do now is when I'm going to go through the other examples, but I'm not going to show you how to calculate the distance. It's pretty obvious how to do it. Okay, I'm just going to write down the actual final distance numbers, and then you can verify for yourself that that's equal. So we have -2, -1.5. Okay, so if I want to calculate this distance, I'm just going to write it down for you. I don't want to insult your intelligence, but we've seen this enough already to figure out how to calculate this. When you do this one, this is equal to square root 24.625. When you calculate this distance, okay, between the second one, we get 1.3906. Okay, so obviously this one is a smaller one, so this means that the membership for the second example is equal to cluster number 2. Okay, now I'm just going to do it for the rest. I'm not going to, I like to move on to something else. So this is the third example would be -1.5, -1. Okay, so when I calculate the distance between, sorry, this is 2, not 1, sorry, 2 and 2. So when I calculate the distance between the third example in each of the centroids, okay, this is both equal to, let's see here, we've got square root 18.125, square root 0.2656. So obviously this one's a smaller one, so therefore the membership for the second example is also equal to the second one, okay? So fourth one, we have 1.5 and 1, okay? The distance between the fourth example to each of these centroids, okay? I'll let you verify this on your own. Okay, this is equal to, we have square root 0.625, and when you calculate this to the next centroid, we get square root 9.765. So this one is a smaller one, so this means that the fourth example gets assigned to cluster number 1. Okay, and then if you do it for the last two, I'm just going to write these down for you. Okay, so the distance between the fifth example and the first centroid is equal to 0.125, and then the next centroid, next one, is equal to quite a large number, 43.515. Okay, so smaller one. Okay, therefore this is equal to the first one, and finally we'll do it for the last example, just for, you know, just to wrap things up. Okay. Oopsie, 2, it's 1. Got carried away there. So this is equal to 0.125 again. And this one is 11.8. Oops, I screwed this up. So sorry, I mixed up the numbers. This is 11.89. Apologies. I just don't know how to copy down a number. And this is 43.515. It's still the same thing though. So this is the closer one, so we get, all right? So now if I want to calculate so now that you take a look here, that, remember the membership for the fourth example was 2, and now it's migrated back to 1, which is nice. So now if you want to calculate the centroids, the updated ones now, there's only 3 examples. I'll let you verify that this centroid is equal to, hold on, going to the next page. Okay, this is equal to 1.667 repeating, and we have 1.5, okay? And then finally, you want to calculate the centroid for the last set of training examples, which is 4, 5, and 6. Okay, when you calculate this, we get minus 1, let's see here. It's minus 1.833 repeating and minus 1.5. Okay, so now I'm going to let you do the third iteration on your own, and you're going to see that the memberships and the centroids don't change. So we've actually found convergence. So these centroids actually represent the 2 clusters. Yes? Yes. 4, 5, and 6. Oh, yeah. Of course. Got ahead of myself. Yes. Okay, good. Yeah. Because the first 3 belong to the second one, the last 3 belong to the first. Okay, good. Thank you. Okay, so iteration number 3, do on your own. But you will see that convergence happens. You'll see that the cluster memberships don't change, and the centroids don't change either. So I put the third one in there just to show you that they actually don't move, and we actually achieve convergence. Okay, so that's it for you. So that's how you'd actually compute this row. So what the code is actually doing that you wrote, this is what you're actually supposed to do in the end. Okay. All right. All right, last question. So self-organizing maps, this shouldn't take very long. It should take hopefully 10 to 15 minutes tops, and we're going to finish early today. Okay? So this is the last question that we have. This is a self-organizing map. So remember, a self-organizing map is a neural network that operates in an unsupervised manner. So the goal is to be able, it's a data visualization technique where it takes similar inputs and maps it to similar areas in the self-organizing map, mostly for data visualization and also to infer some structure in your data. Okay, so we have this self-organizing map, so we have 2 features. Okay, we also have a one-dimensional self-organizing map. And the positions are encoded by the numbers that are directly inside each of the neurons. So this is position 1, position 2, and so on and so forth. Okay, so we have the following examples. We have 2 examples, 2 features each. So 1, 2, 3. This is x1 and x2. So we have -1, -0.5, 0.5, and 2, and -3, and -3. Okay, so let's suppose we randomly shuffle the data. So we shuffle the data. In the problem set, it tells you to do this, and I give you what the order of the shuffled data would be. So shuffle the data, and let's assume that the order would be the second example, the first example, and the third. Let's say this is what the data, this is what the order would be, and it says that in the problem set itself. So let's assume they randomly shuffle, and this is the order that we get. Okay. Also, we are given the following parameters. So we are given sigma 0, which is equal to 2. This would be the rate of decay. So remember, when you update the weights for each of the neurons, you have a radius of where to update. So this will make sure that the radius shrinks over time. So the updates are only incremental local to the actual node itself. And then you also have the learning rate initially, which is 1. And the learning rate should decrease over time. You also have the shrinking parameters for each of these parameters, which is tau 1 is 5 and tau 2 is 3. Okay, we also have initial weights. So a lot of things are given here which are initial. Okay, so these weights are defined in the same feature space as the features in our input. So we have the following initial weights for each of the neurons. Okay, so we have 0, 0.5. This is 2 and 0, and 4 is 0 and 0. Okay. So we initialize the weights to be the same size as, the same length as the actual feature, training example feature itself. Okay, so we have this. What we need to do is we have to compute 3 iterations of SOM training. Okay. So if you remember from the self-organizing map examples, each iteration would be going through just one example. This is stochastic gradient descent. Okay? So one example is one iteration. So basically it's telling us to just cycle through each of these examples. Okay. Okay. So iteration 1, we select the second training example. In this case, it's equal to 0.5 and 2. Okay? And also the current time is equal to 0. So this is initially, this is where we're starting up. So if you remember from self-organizing maps, the first thing you have to do is find what is known as the best matching unit. Okay, so what you're doing is you're going to take this training example and figure out the distance between this example with all the weights in your self-organizing map. And you choose the neuron that has the smallest distance. It's pretty much almost like k-means, except that you're not doing it in terms of points now, you're doing it in terms of weights. All right? So the first step is to find the best matching unit, or the BMU. Okay? And how do you do that? Well, what you do is you figure out, so you have this, so let me see here. So you figure out the distance between the example and each of the weights currently, okay? I'm going to call this W1 of t because right now the weights are updating, so this is at time is equal to 0. In this case, the weights, let me just take it here so you have 1, 1. So what's going to happen is that you take the distance, so we have 0.5 minus 1 squared plus 2 minus 1 squared. It's 1, 1, I believe, right? 1, 1, yep. Okay, so when you calculate this, this becomes 1.25, okay? And then you calculate the distance between the second example and the second weight currently at this time, right? So weight is 0, 0.5. So we have 0.5 minus 0, and then plus 2 minus 0.5, okay? When you calculate this, this becomes 2.5, okay? Find the distance between the second example and the third set of weights currently. So this is 0.5, and then what was it? It was 2 and 0, I think. Was it 2 and 0? Yeah, 2 and 0. Sorry, this is 0. Sorry, it looked like a 6 for a minute. So minus 2, okay? And then plus 2 minus 0, okay? And in this case, we have just 6.25 square root, all right? And then finally, we need to calculate the distance to the last set of neurons. So this is 0.5 minus, and then what was it? It was 0 and 0. This case, this is 4.25. Okay, so which of these is the smallest? This one here. Okay? Because this is the smallest, this belongs to neuron 1. So the best matching unit is neuron 1. Because out of all the weights, it matched with the first set of weights the best. So that's the output for that. Okay, so that's the best matching unit. So now what you need to do next is you have to do updates. So what you have to do is you have to update the weights so that if you were to present this input into the self-organizing map the next time, you want to be sure that it maps to the first neuron. So we're doing those updates to make sure that the inputs are going to be put into the right areas for the self-organizing map. Okay, so B, update weights. Okay. So this is just for the 1D case, all right? So if you want to update the weights for the next iteration, you take the previous iteration, okay, and then you have to apply a learning rate, alpha, that is seen at that current time. And then you also have to apply a radius of decay when you're updating the neighborhood of weights that surround this neuron. So X, and this is I, T, and then stop doing that. And this is X minus. Okay? So in this case, yep. All right, this is good here. Okay. So this would be training example number 2, and then this will be weight for neuron I, okay? So what's going to happen is that what I like to do first is I like to calculate each of these. So alpha t, if you recall, is equal to alpha 0 e to the power minus t over tau 1, okay? I'm pretty sure. I'll just double check to see if that's right. And yes, okay. So in this case, remember time is equal to 0 currently. So we are currently we're currently at the initial step. So in this case, alpha 0 is equal to, well, alpha 0 is equal to what? It was 1, right? I'm pretty sure it was 1, yes. So this is 1 times e to the minus 0, and then tau 1 was equal to, I think it was 3. It was 3, yes, 3. In this case, this is just equal to 1, so in this case we get 1. Okay. Now I also like to calculate the radius of decay as well. So this is sigma 0 e to the minus t over tau 2. In this case, this is 2 e to the minus 0 over 5. That's equal to 1 again, and then we get 2. Okay. So if I want to calculate this weight, I'm going to do it for the first one, is equal to the previous one plus alpha t I know already is equal to 1. Times, okay, so this one here I haven't defined yet. This defines the actual radius of decay. So this is equal to e to the minus. Okay, this I calculated already. So this stuff goes here, okay? And now these numbers, what this means is that it's the actual position themselves. So NX is the position of the BMU, okay? And this is the position of neuron I. Okay, so the position of the BMU, if you take a look, it was equal to just simply 1. This is the BMU right here. So in this case, you would have substitute, so you have e to the minus, and then 1 minus 1 squared divided by 2, and then sigma t is already 2, so this is 2 squared. And then x, the training example, is equal to, what was it, 0.5 and 2, right? 2. Subtract the current weight. So this is just W10. And I'll substitute everything after. Okay, so this is what I need to compute. So 1 minus 1 is actually 0, so e to the 0 is 1, so we get rid of this. So the update that you're going to apply is 0.5, 2, plus 1, and then 0.5, so not 0.52, this was, what was it? It was 1, 1, right? Sorry, let me see here. Sorry, 1, 1, not 0.5. So 1, 1, 0.5, 2, subtract 1, 1. Okay? So when you actually compute this, what you get is by fluke the same thing. That's nice. Okay? That's good. So that actually helps us a lot because we want to make sure that the weights for the first neuron don't change because that's what the first input maps to, which is pretty nice. That's good. Okay? Now you want to update for the next weight. So we have W20 plus alpha, right? In this case, we have t. Oh, sorry, you know what? It was h of x. Okay, so I, t, and then t is 0 here. Let me just replace that. This is, yeah, t is fine. Good, 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 sorry. So we have 2, 0, and then we have alpha 0, and then h of x 2, and then 0, right? This is I, this is t, and then x subtract. Okay, so the next set of weights, W2, let me take a look, it was 0, 0.5. So we have 0, 0.5. Alpha 0 was simply 1, okay? And this is, let's see, e to the minus squared, and then 2. This is t. All right, so t is equal to 0. Let me just, okay, good. And then x was 0, 0 point, not 0 point, it was 0.5 and 2. Subtract 0, 0.5. Okay, so this is the position for the BMU. This is 1, and this position for the neuron is 2. This here is 2, okay? So what's going to happen is you'll get 0, 0.5 plus, and then you have 1 divided 2 times 2 squared is 8. So you get e to the minus 1 over 8. Okay, and then this would be 0.5 and 1.5. So when you calculate this update, we get to be 0.4412 and 8237. Okay, that's the update for the next neuron. Now we do it for the other one. So we have to do the third and the fourth one. So W30 and then plus alpha 0, h of x. So I is the third neuron and the time index is 0. And we have, sorry, I hate it when it does that, x minus. Okay, so W30, the initial weights were 2 and 0. Okay, so we get 2, 0 plus alpha 0. This would become 1, okay? And this is e to the power, and then 2, and then, sorry, this is 0, okay? And then x would be 0.5 and 2 minus 2 and 0. Okay, remember, this is the best matching unit positions. They match position 1. This number here is position 3. This is neuron 3. And this here is 2. So when you calculate this, this becomes 2, 0, plus, and then we have 2 squared. This becomes e to the power minus 4 over 8, which is e to the power half. So let me just put 4 over 8 here. and this becomes minus 1.5 and 2. Okay? So when you calculate this, this update becomes 1.0902 and 1.2131. Okay? Finally, you're going to do this for the last one. So okay, so this one was simply 0, 0, okay, plus, and then we have 0. This is 1, and then we have e to the power, and x minus ni. Okay, and this becomes x is 0.5 and 2, and you're just subtracting with 0 and 0, which doesn't do anything at all. Okay, so this is 1, this is 4, and the bottom here is 2 again. So what you're actually computing is this goes away, there's nothing here. So we have e to the power, so let me see here, 1 minus 4 is 3, so you have 9 over 8, and then 0.5 and 2. So when you calculate this, this becomes 0.1623, 0.6493. Also like to note that the solutions that I put online are incorrect. These are the actual correct solutions, and I'll update the problem set when I get home. So if you have downloaded the problem set for this particular one, you'll have to re-download it when I update it. Okay? All right. I'll do one more iteration, and then I'll let you do the last one on your own, and we're going to call it quits. Okay, so iteration 2. What you have to do next is we're presented with the second training example, which would be the first one when you reshuffle everything, which is -1 and 0.5 transpose. The time index currently is 1, okay? Now, what we need to do is I'm going to write down all the weights that were currently updated. So these were the updated weights at the current time step now, okay, which is 0.4412 and 1.8237. Okay, we're almost done here. And then hopefully I'll be able to end a few minutes early. 0.902 and 1.2131. And finally, we have these update weights, which is 0.1623 and 0.6493. Okay, so those are the weights now. This is from the previous iteration. We have this example to take a look at. So what we have to do now is we have to find the BMU. We have to find the best matching unit. So you have to take this training example and figure out which of these weights match in terms of it best matches. So you find the one with the smallest distance. So you find the distance between the first example and the first set of weights currently at this time. Okay, so in this case you find the distance. So we have -1 minus 0.5, okay, plus, and then 0.5 minus 0.5 and 2. Okay, so when you calculate this distance, we get square root of 4.5. Okay. You calculate the distance from the first example to the next set of weights. Okay, when you do this, we get, what was that? It was -1, and then the weight was minus 0.4412. Okay, plus, and then we have 0.5, subtract 1.8237. Okay, so when you calculate this one is square root of 3.8295. Okay. So that's the distance between that and the second set of weights. We do it for the third one for the same example. Okay, so we do -1, and this was 0.5. Okay, so the second set of weights was 1.0902 squared, plus, and then 1.2131. Okay, this is equal to square root 4.8774. Okay, last but not least. So if you ever get confused about figuring out which order you're subtracting with, what I like to always do is I like to write out each component separately. So I like to write out the training example first. So I know that the training example is -1 and 0.5. Okay? And then the weights after, in this case, if you take a look above, you just make sure you pair up the coordinates. So it's 0.1623 squared plus, and then minus 0.6493. So that's how I like to do it. If you ever get confused about how to write this in this order, make sure you just write out each component separately. So do the x and the y for the, the example, and then the x and y for the weight, and then you just add everything up. Okay? So when you calculate this distance, this one is equal to 1.3733, so square root 1.3733. Now, if you take a look at all of these distances, 1, 2, 3, 4, this one here is the smallest, okay? So the BMU is neuron 4, okay? So this means that the position for the best matching unit is position number 4. And I like to explicitly put that up above. So the best matching unit in this case is 1, okay? So this is the position itself. If this was a 2D grid, then you'd have a 2D spatial coordinate, but anyway. So last but not least, we're gonna update the weights, all right? So update the weights. This should take only a few minutes, and we're going to end a little early today. Okay? So when we update the weights, what you have to do now is you just have to apply the same equation that we did before, but you're doing it on the most recent update. So we need to calculate the the learning rate decay. So this is alpha 0 e to the power minus 1 over tau 1, which I believe is 5. Okay, let me just double check to be sure. 5 and 3, if I got that right. Yes, oops, I mixed that up. So this is, it doesn't matter here. This should be 5 and 3, but it doesn't matter because the time index is 0 anyway, so it doesn't matter. At that point anyway. Yep, 5 and 3, my bad. So we have 5. In this case, this is equal to 1. So this number here is simply 0.8187. Okay, if you want to calculate the radius of decay for the next time step, this is sigma 0 minus 1 over 3. This is equal to 2 from before, so when you calculate this, this is equal to 1.4331. Okay, now you have to do the updates. So once we do the updates, that's it. So do the updates. So to the next time step, you take the previous time step plus alpha 1. Let me just do I here just to make this general. Okay, so 1 and then h of x 1, sorry, I 1, okay, and then x. Okay, so to do this for the first set of weights, the previous set of weights was 0.5 and 2, plus this was 0.8187 from before, okay. This guy's going to be a little complicated, so you have e to the power minus 2 squared, okay? And this becomes 0.5, oh, sorry, this was, the train example was minus 1.5, sorry. And then 0.5 and 2. Okay, so the best matching unit was 4. The spatial location is 4. This is equal to 1, all right? So what's going to happen? So when you substitute this and this is equal to 1.4331 inside there. So you have to square that and you multiply by 2. When you add up all this together, okay, I won't bore you with the details, you actually get minus 0.0043 and 1.4145. Okay, do the next set of weights. Okay, so it would be the previous one. So in this case, it would be 0.4412. 4412, 1.8, what is it, 237, okay, plus 0. So this alpha stays constant the entire time, but this radius of decay term will change to, and then sigma 1 squared, okay. Remember the best matching unit was 4. This node of this position is equal to 2. And then this here is just 1.4331. You just, remember, this is just that by itself. You have to square it, multiply by 2. And then finally, we get minus 1, 0.5. Subtract this, so 0.4412 and 1.8237. So once you do all this, when you calculate this weight, set of weights, we get, what is it? Looks like I copied down the wrong. That's weird. Oh, okay. I'll have to fix. Okay. This apparently I copied that down wrong. So I'll have to get back to you. So This, I'll have to get back to you, because when I did the example here, I copied down the first and the second set of weights, so I'll have to update that for you. So this is wrong in my notes, so I'll leave that blank for now. So, okay, so I'll just write these ones down just to be sure. So we have, I'll just write these down so you can, so let me see here. So we have 1.0902, so this is the current iteration. 2131, okay, minus, and then 0.8187. So we have E minus NX minus NI squared, and then, okay, and then this is minus 1, 0.5. So you subtract this with 1.0902 and 1.2131. Sorry. Almost done here. Okay, so when you get these, the weight you get here is, let's see, what was it? It was minus 2.2513 and minus 0.5271, actually just positive. Yes, no, sorry, no. 0.5 and then 7.54, okay, sorry. 4, okay? All right, and then finally, let me just write down, so this was 4, this is 3, this is 1.4331, okay? And then finally, we have this one here. I'm just gonna write this out. This is 0.1623, 0.6493 minus, and then we have 0.8187. And what's gonna happen here is e to the minus nx minus ni divided by 2 sigma 1 squared. In this case, both of these match. So the best matching unit and the position of this neuron are both the same. So this all gets canceled to 1. And then you have minus 0.5 here, and then minus, what is it, 0.1623 and 0.6493. So when you add these all up, the final weight that you get is minus 0.7893 and 0.5271. Okay, and then I'll let you do iteration 3 on your own. So you pretty much know how this works now. Okay, so this, unfortunately, I don't know the answer to this. I copied it down wrong. I copied down the first one and the second one to be the same, so that's obviously not it. But I will update this one for the problem set. I'll put that up online. Okay, and that's all I have here. So that's a self-organizing map example. Okay, any questions here? Okay, so that is it for today. So next time I see you will be your final exam, which is on the 26th. So unfortunately, I'm canceling office hours today. I have unfortunately have some personal matters to attend to. But if you have any questions, by all means, please email. Unfortunately, I will not have any office hours until the final exam. So if you need to get in contact with me, by all means, please email. I should be able to respond to you very quickly. All right? So I will not see you until the final exam. So all the best. Best of luck in studying, and I'll see you on the 26th.